Okay, this is part 3 of my lecture on chapter 7. Here we're going to introduce to you the central limit theorem. It's kind of an important theorem that we're going to rely on for much of the remainder of this chapter and the next couple of chapters. Central limit theorem. What is the summary? Summary of central limit. The sampling distribution, okay, of the sample mean. Remember, we take 10 samples, then we could calculate the average of the samples, or 10 of them, right? 10 averages. And the distribution of these sample averages approaches the normal distribution as the size is sufficiently large, usually around 30 to 50, depending on the skewness and the source of the information. I think this book says 30, other books say 50. Just remember that. I think I learned it at 50 years ago. One important statistical theorem that describes the sampling distribution of sample sums and the sample averages. Okay, well, I didn't say it applied to the sums, but it does as well. All right. So let's go through how this works with the following example. Okay, we're going to see quickly how rolling a die, first time you roll 1 die, next you roll 2 die, third time 3 dies and 4 die. Okay, you will soon see that the average and the sums, basically the distribution of the average and the sums, become normally distributed. All right. Suppose you toss 1 die. So you throw 1 die. Okay, so this means that you throw 1 die, so you just take like 1 sample, right? The random variable x is the number observed on the face value. Yeah, so this random variable x could take one of 6 value. You could show 1, 2, 3, 4, 5, or 6. And each of this has 1/6 probability. Okay, so the probability distribution is uniform. See, it looks just like this. You roll a die or throw a die. You could show 1 through 6. Each has equal likely probability of 1/6. Okay, the shape of the distribution is discrete and uniform. Okay, it's symmetric around the mean of 3.5. The mean is 3.5, right? And with the standard deviation of 1.71. You can calculate those things. All right, now let's take 2 dice. Okay, instead of 1, we're going to throw 2. So now n is equal to 2 from the population. Toss 2 dice and record the sum below. Okay, so here's the 2 dice that you throw, 1 through, and then the first die you could get 1, 2, 3, 4, 5, and 6, and second die you get 1 through 6. Right? You throw 2 dice, and then you could show 1 on one of the first die and a 6 on another die, and then you add the numbers, you sum them. Okay. So the sum is, if you get a 1 and a 1, it's a 2. 2 and a 2, it's a 4. 1 and a 2, it's a 3. So that's what this box tells you. 6 and a 6 is a 12. So these are all the possible sums. You get a 2 1 time, 3 2 times, 4 3 2 times, 4 3 times, 5 4 times, 6 5 times, 7 6 times, 8 5 times, 9 4 times, 10 3 times, so on and so forth. Okay. Get the mean of all possible outcomes by dividing by the number of dice, or 2. Okay. So this is the sum, and we could get the mean. Okay. The sampling distribution is of the sample means with 2 dice. This is right here. So 2, you divide by 2, right, to get the average. When you throw 2 dice, Okay, you get a 1 and a 1. That means the sum is 2, but you divide by 2, and that means you got a 1. The average is 1. Okay? When you roll a 2 and a 2, okay? Right? Then the average is 2 because the first die you got a 2, second die you got a 2, so on average, yeah, you got a 2. It's the same thing. If you got a 2 and if you roll 2 dice and the first die came out as 1 and the second die came out as 2, the sum is 3, right? You divide it by 2 and the average is 1.5 because the first die got a 1, second die got a 2, so you got the average is 1.5. That's what they're saying. Okay. So the first time you rolled the 1 and a 1, you got a 2 divided by 2 is 1. Okay. 3 divided by 2, you got 1/5. That's the average. I mean, 1.5 is the average. And you have 2 out of 36. That is 1.5 average. How do we know that? Right here. This box contains 36 sums. Okay, that's the 36 different possibilities you could get when you roll 2 dice. The one possibility, the lowest one, is getting a 1 and a 1. Okay. You could get 3 twice, 2 possibilities of getting a 3. The first die, you got a 1, and the second die, you got a 2. Or the first die, you got a 2, and the second die, you got a 1. So there's 2 chances of getting a 3, 3 chances of getting a 4. And that's what shows here. Okay, it shows you the averages and then shows you the number of chances you could get these averages. Okay, and then plot the relative histogram or the relative frequency graph. So here on the x-axis, you show the average, and the y-axis, you show the probability of getting these numbers. Okay. So for example, getting a 1, you have 1 in 36 chance. That's this. Getting a 1.5, you got 2 in 36 chance. Getting a 2, you have 3 in 36 chance. And you could see it's when you plot the relative frequency distribution or the histogram, it looks different than here. Used to be a flat uniform shape. Now it's kind of like a pyramid shape. Okay. Here again, the average of these averages is 3.5. Mu is 3.5. The average of the average is 3.5. Okay. So we're going to continue this process. Next, we're going to roll 3 dice and then 4 dice. And then rather than going through all of the detailed analysis, I'm just going to show you what the histogram looks like. For if you roll 3 dice, it's still going to center at 3.5. And now look at this. Okay. It's getting more and more normally distributed, or looks more like a bell-shaped curve. Now let's do 4 dice. Okay. Looks really like normal distribution. You could see even with 3 and 4, a sample of 3 and 4, n equals 3 or n equals 4. Okay, when you roll 3 dice or 4 dice, the distribution of the sample mean becomes fairly normally distributed here. Okay. This convergence to the normal distribution is the central limit theorem. So here's the central limit theorem, the formal definition. kind of already told you, if a random sample of n observations are drawn from a non-normal distribution, doesn't even have to be a normal distribution, with a finite non-normal population, non-normally distributed population, okay? We don't have to have the population to have a normal distribution, okay? With a finite population mean of mu. So the population could have doesn't have to be normally distributed, okay? But it has some sort of mean of mu and a population standard deviation of sigma. Then when n is sufficiently large, meaning we got the samples, the number of samples are sufficiently large. A sample size, I'm sorry. If the sample size is sufficiently large, let's do this again. The sampling distribution of the sample mean is approximately normally distributed with the mean of mu standard deviation, or the standard error of the sample mean, is sigma divided by square root of n. Okay. All right, let's say, let me try this again. If random samples of n observations, sample size is n, are drawn from even non-normal populations with finite population mean of mu, the parameter, the population mean parameter mu, and a population parameter standard deviation of sigma, when the sample size gets large, the sampling distribution, the distribution of the sample means is approximately normally distributed with the mean of mu, the population mean, right? The mean is equal to the population of mean. And the standard deviation of sigma divided by square root of n, okay? And the approximation becomes more normal as n becomes larger. So as n becomes larger and larger and larger, it becomes very, very, very more normally distributed, more classic normal bell-shaped curve. This central limit theorem also applies to the sum of the sample measures. So not only does it apply to the sample mean, but also the sum, okay? And as n becomes large, the sum has an approximately, the sum of the sample has an approximately normal distribution with a mean of n times mu and a standard deviation of this, sigma divided by n to the 1/2 power, meaning sigma divided by square root of n. Okay. So when is the sample size large enough? Okay. If the population is normal or normally distributed, then the sampling distribution of the sample mean will also be normally distributed regardless of the sample size. So if the population is believed or is known to have it be normally distributed, sample size could be very small. Okay. When the population is approximately symmetric, the sampling distribution of the sample mean becomes approximately normal for a relatively small value of n. Okay. Remember our dice rolling example above. We only needed n equals 3 or 4 to show that the sampling distribution became really close to a bell-shaped curve, if not equal to one. Okay. When the sample population is skewed, the sample size n must be larger. Okay, so if we have some weird looking sample distribution, population distribution, if the population distribution is all wacky looking, basically you need about 30 in your sample. You need 30 observations in your sample. Other books say 50. Okay, so key is about 30 in this book. But in real life, when you work with others, maybe they learned it from a different book that says 50. So just be aware of that. All right, let's keep going and let's do an example of, okay, well, what we learned. How is it useful? We'll do these examples to show how this information is useful. Example 7.4. The duration of Alzheimer's disease from the time symptoms first appear until death ranges from 3 to 20 years. And the average is about 8 years, with the standard deviation of 4 years. Okay. The administrator of a large medical center randomly selects the medical records of 30 deceased Alzheimer's patients from the medical center's database and record the average durations. Find approximate probabilities for the following events. The average duration is less than 7, the average duration exceeds 7, and the average duration lies within 1 year of the population mean of 8. Okay, so let's solve through example 7.4. Okay. Okay. The average, okay, we'll call that the mu, is 8. And the standard deviation, or sigma, is 4. Okay, that's what we know so far. And we know n is 30. Okay, so sample size is 30. We could apply the central limit theorem. Okay, and they want us to find the following: the probability of x, okay, being less than 7 years, the probability that the average duration x is greater than 7 years, and the probability that the average duration lies within 1 year of 8. So the probability that it's between 7 less than x is less than 9, I believe. Okay, 1 year, 8 is the average. So minus 1 is 7 and plus 1 is 9. Okay, so they want you to find these 3 probabilities. Okay. All right, so let's do this. To find the first one, the probability is less than 7. Here's a graph of a normal shape distribution with the average of 8. Okay, this is what we have. And what they want is, here's 7. We know this is 8 right here. 7 is below 8. That's the cutoff. And they want you to find the area of the shaded region, or the probability that the sample mean is less than 7. The average duration is less than 7. So they want you to find the area of the shaded region. This is normally distributed. So all we have to do is apply the normal distribution formula. And in Excel, that's norm.dist. Okay. Because we want to find the area of the shaded region, it's the cumulative. Okay. So we're going to have to remember we want the cumulative from the really extremely small all the way up to 7. Okay. So we want to use this formula. The first number we want to put in is x, which is 7, the cutoff. The mean, which is 8. The standard deviation, okay, that's the standard error. And cumulative, we want true. But we haven't even figured out the standard error, so we can't do this yet. Okay. So let's do that first. Okay, I forgot to do that. Let's scroll this down. Standard error. This is the standard deviation divided by the square root of the sample size. Okay, if you scroll up here, standard error or the standard deviation of the sample mean is equal to the standard deviation that they give you, divided by the square root of the sample size. Okay. So it's 30 to the 0.5, close parentheses. That's what it is. So let's do this again, equal to. And for the standard error, we know what it is. We're going to plug in this number here. Enter. Should be 8.55. This area right here should be 8.55. And let's see, norm.dist, that's what I used. 7, mean, standard error, and true. And it's 0.0855, 8.55%. Now let's do the next one, which is x being greater than 7. What's the probability of x being greater than 7? Well, we know the probability of x being less than 7 is this. So greater than 7 is equal to 1 minus this number, which is 91.45. Okay? 91.45. Now remember, because we're talking about continuous random variables, we could get sloppy with the x being less than equal to or x being less than, okay? Or x being greater than equal to, x being greater than only, because that infinitesimal difference has no effect on these calculated probabilities. This is not true for discrete variables, but for continuous variables that are here normally distributed, so they're continuous variables, doesn't matter, okay? We could be a bit sloppy. Now here, we have to find the probability of x being less than 9 but greater than 7. Visually, this is what it looks like here. We have to find the area of the shaded region, okay, which is cut off between 7 and 9. And the way you could do it in Excel is you find the cumulative up to 9 and subtract the cumulative up to 7 to get the shaded area. So we're going to do that in 2 baby steps. Find the probability of x being less than 7 and find the probability that x is less than 9. Okay. So the probability of x being less than 9 is norm.dist. 9, comma, mean is mu, comma, standard deviation is the standard error, not the standard error, comma, cumulative, we want true because we want the area all the way up to the cutoff of 9. So everything from x being negative infinity all the way up to 9. Okay, all of this right here. And the probability of x being less than 7, we've already calculated that. So I'm going to just make it equal to that. Okay. So this is just this dude minus this dude, which is 82.91. It's just the area up to 9 minus the area up to 7, which is the yellow area, 0.8291. 82.91. Okay. All right. That's basically what we are going to do for a lot of the remainder of the textbook, okay, is calculate these type of probabilities. And you need to remember how to apply the tools that you have. Specifically, I'm teaching with Excel, so I'm going to focus on applying the Excel to calculate the answer we want. Okay, one is a basic one where we just do to calculate the probability of x is less than 7. We just apply the normal distribution function in Excel as is. to get x's probability of x is greater than 7, we have to calculate this probability of less than 7 and subtract 1 from there. And then to get, say, something in between two numbers, we have to calculate up to one number and subtract up to another number. That's how I got 82.91. Okay. Section 5, how to assess normality. We're not going to cover this for the midterm or the final, so we're going to skip through this, okay? And let's go to the next one, which is section 6, which is sampling distribution of the sample proportion. The probability, so what is sample proportions? That is, you collect a sample and see how many people, what fraction of people will vote Republican. Or you collect a sample and say, what fraction of people are Christians or Jewish or women or Korean, okay? You want to calculate these fractions, okay? What fraction of the people are considered poor, considered super rich? Okay, that's what we're doing when we're calculating sample proportions. So properties of the sampling distribution of the sample proportion. It's going to have the same type of properties, okay, as we just discussed for the sample mean and the sample sum. The proportion is a ratio. It provides information on the fraction of the population that has a specific characteristic, okay? Proportion of x within n is equal to x divided by n, right? So examples, proportion of defective parts to total parts in the assembly line, the proportion of all people entering a retail store who do not make a purchase, proportion men in the United States. These are all proportions. Or fractions, fancy way of saying fractions. Sample proportion is equal to P with that little caret on top, or P hat. We call that P hat. Okay. Suppose we have a binary random variable x with a probability of P of x. The mean is equal to n times P, and the standard deviation is n times P times Q. What is Q? That is 1 minus P. Okay. So we have a binomial random variable. That means it could take yes or no, or true or false, or black or white, or red or purple, just two values. And the probability, okay, of this is of taking on a specific value is P. Then the probability it doesn't take on that value is Q, or 1 minus P. So the standard deviation, n times P times 1 minus P, or Q, to the 1/2 power, or square root of that. So the sample proportion is x expressed as a proportion, which is x divided by n. X is the number of the sample that takes on this specific characteristic that we're looking for, divided by the sample size. So if we collected data on 100 people, 55 are women. The proportion of women is 55 divided by 100. Duh, hopefully. Example, number of women, x is equal to 4, n is 10. So the sample proportion is 4 out of 10. Okay, the expected value of the sample proportion is the true proportion of the population. Okay, P is the population proportion. The standard deviation, or the standard error of the sample proportion, okay? This is the sampling distribution of the sample proportions. So the standard deviation of the sample proportions is the following. For finite population, it's P times 1 minus P, or Q, P times Q divided by n, square rooted, times this, this normalization or correction factor, finite population correction factor. For the infinite population, you don't have this finite population correction factor needed. Okay. Again, we needed this for unbiasedness and in the application of the central limit theorem. But you really only need this for certain under certain conditions. Okay. And specifically, finite population standard deviation is treated as being infinite if little n, the sample size, divided by population size, is less than equal to 5%. Okay. The sample is small relative to the population, small, I don't know, 5% or less, then we could disregard this finite population correction factor and just use the simpler calculation formula for the standard error or the standard deviation of the sample proportion. Okay. When the sample size n is large, the sampling distribution of the sample proportion can be approximately normally distributed. Yeah, why? Because of central limit theorem, same as above, that we learned for the sample means and the sum. And the condition, okay, remember the sample mean and the sum was you need about 30 observations. Okay, for here we need n times b to be greater than or equal to 5, or n times q, or 1 minus p, to be greater than or equal to 5. Okay, so this is the condition. All right, so let's do this. Let's do example 7.10. In a survey, 500 parents were asked, so n is probably 500. Sample size is 500. Were asked about the importance of sports for boys and girls. Of the parents interviewed, so of the 500 parents, 60% agreed that boys and girls should have equal opportunity to participate in sports. So maybe this is P, maybe this is Q, I don't know, but let's say it's 60% is P for now. Describe the sampling distribution of the sample proportion of parents who agree that boys and girls should have equal opportunity. Well, let's see, okay? Okay. So let's see this. We know the sample size is 500. We know P is 60. Okay, so the Q is equal to 1 minus 60, or 40%. The mean, okay, mu, let's calculate the mu in the standard deviation of P hat, okay? So the mean of P hat, if we look up here, well, that's equal to the population proportion, okay? It should be equal to P. And the, so this is actually P hat, I'm sorry. And this is actually Q hat, okay? Because these are from the samples. The 60% is from the sample, and the 40% is from the sample. So these, I should have denoted it better and do P hat and Q hat. All right, and the standard deviation of P hat, do we have to do the correction or do we not? Okay, well, theoretically, there's a finite number of parents, so we might have to do the corrections. But if n divided by big N is less than or equal to 5%, we don't have to do the correction. Okay, little n is 500. Well, how big is big N? Well, we know the population size in the United States is 350 million. That's I mean, I'm sorry. The number of people in the United States is 350 million. Assuming, let's say, I don't know, that's number of people. How about the number of parents in the United States? Well, let's suppose 350 million. Okay. And as the number of people. So let's think about this. Divided, let's say, there's the average family has about 2.1 person, so divide by 3. Okay, so let's say 160, I don't know, let's say 116 million people are adults. Okay, I don't know. Let's just say, even at the worst case, let's say divide by 10, 35 million are parents. I think it's more than that. So little n divided by big N, this is equal to 500 divided by 350. Yeah, that's less than 5%. Yeah, that's less than 5%. So we could safely drop the finite population correction term, and then we could calculate the standard error or the standard deviation of p hat as equal to p times q divided by n. Okay. Okay. Let's do that first. I know I'm using p hat for now, but I'm just want to populate this first before we go down and read the question some more. Okay. All right. Okay. So the sampling distribution, we would have to use this formula here, just like above. We could probably safely say that we could drop the finite population correction term, and we would have to we could use this formula, but we don't know what P is, we don't know what Q is, so we can't calculate the standard error, but I calculated for you an approximation using P hat and Q hat, okay? Now let's do example 7.11. Refer to example 7.10 and suppose someone claims that the true proportion P is equal to 0.55. Now, P, not P hat, P, and Q is equal to 1 minus this. Now we could actually calculate the standard error, right? We could calculate this for real. This is equal to, okay, it's P times Q divided by N, and the whole thing, I believe, is square rooted. To the 0.5. Okay. Yeah, close enough. Okay. Let's make sure. Yeah, P times Q divided by N, the whole thing is square rooted. Okay. What is the probability of observing the sample proportion as large as or larger than the observed sample proportion of 0.60? Okay, that's the question they want you to find. One thing we did find is a standard error. We need that to find this anyways, okay? All right, so what they want you to find is the probability that X is greater than, large as, or greater than or equal to 0.60, okay? So if we want to show that visually, okay, we know that the true population, someone told you that, is 0.55. We found from our sample of 500, P hat to be 60%. And they said, well, what is the probability of being greater than or equal to 60%? So what is the probability of being in this shaded region? In order for us to calculate that probability, we need to first find, okay, we know this is normally distributed. So we need to first find X that is less than 0.60. And then we could subtract 1 from that to calculate the area of the shaded region. So this is norm.dist, and X is 0.60, comma, the mean, the true mean is 0.55. That's the mean. And the standard error is this that we calculated, and we want to do true. So this is equal to 1 minus this. Okay. So it should be 1.23%. And that's what we calculate. That's the solution there. All right, there's an example that you guys could do yourselves. Okay. And section 7, we're not going to do. And we are done. Yep, we are done. This is the end of the lecture on chapter 7. This is part 3 and the remainder of this chapter. Okay, have a nice day. Huh? Oh, I need to stop recording. Okay.